Let's turn now to our first guest, Julie Bernauer from NVIDIA. Julie joined NVIDIA after 15 years focusing on machine learning for computational biology, but now she builds and operates high performance and deep learning supercomputers for NVIDIA. Today, she is going to share some insights into the Selene supercomputer. Julia, are you there?
Thanks, Mike. It's a
Now,
pleasure to be
Julie,
here.
you actually build supercomputers in your current job. In a previous lifetime, you did a lot of computational structural biology. And the latest thing that you've been working on, and you're here to talk to us a little bit about today, is the Selene Superpod. And you've got some examples from that. To just very quickly, tell us how you get from computational structural biology to building supercomputers.
Oh, that's a great question. I used to be one of those, users using making application for a lot of hours to be able to do their research. And I guess at some point I figured I knew a little bit too much about GPUs, AI, and I wanted to try it myself.
All right, so let's get into this. We're on the schedule today. Uh, Tell us about Saline. What is it made out of? I know there's some great things in there with the DGX and Superpods, and you've got some DDN technology. So let's walk through that.
Okay, so let's start. Selene is a DGX Superpod deployment. So as of November 2020, Selene was the first MLPerf commercially available system. It was the fifth supercomputers in the top 500 and fifth on Grain 500. So basically, Selene is the supercomputer that NVIDIA uses for our own purposes, right? We build it all the way up from NVIDIA technology using DGXA 100. We're going to come back to this a little bit better. And we try to see how good could we make a supercomputer, and we're going to see also after how good can we make it, and also give everybody a way to have one like us, right? So NVIDIA sells servers and sells pods, and we're going to discover together today what is the pod architecture.
So the DGX is fast, I take it. And how do we think about supercomputers in terms of rating them against each other, and what makes something number one versus number five?
Oh, that's a good question. So to build a cluster is just not putting a bunch of computer together. You need a lot of things. You need to make sure the GPUs, for example, as far as NVIDIA is concerned, can work
Mhm.
with each other very, very well. So we're going to see a little bit of this later. But what's very important in a supercomputer is each server, the capability that each server has, but also how they bring together with the fabric. And see, we're going to see that we're using NVIDIA networking technology, and we're using 200 gig HDR IB switches. And we're going to show you how we put those 560 systems together and all that 14 petabyte of all-flash storage to make sure they can all access the data and exchange data with each other for the best DL possible.
So you really got to have all the parts working in concert, and to really drive those GPUs at high capacity, get every last ounce of power out of this. What are some of the things that you've maybe at a high level learned about building supercomputers, just
Oh,
as we go into this?
we learned a lot. So actually, I was planning to show that. Basically, it's at NVIDIA, we feel that you can only do something yourself to understand all the challenges the customer goes through, right? And so we learned about speed and feed, thermal and power design, and interconnect design in the light of deployability. So basically, it's, you see a lot of supercomputers are being brought up over several years. Here we had a real objective of getting very, very fast on the floor, being very flexible, and being able to extend it. Because in AI, the fastest you deploy, the fastest you're competitive with the world. And the competition right now is very, very fierce.
Oh, so that's great. So again, it's not just even putting together all the technologies. You've got to actually be able to get it out there fast and get it moving. Tell us now a little bit about some of the more particular parts about what went into this SuperPod architecture, and some of the cool things that you think that people should take notice of.
Okay, so first we need to operate it. And the reason we need to do that is because this supercomputer is part of clusters at NVIDIA, and we need those clusters for our actual everyday work, right? So basically, we need to integrate all the tools that deep learning researchers use on a daily basis, like
Mm.
GitLab, Docker, etc., with supercomputers that are traditionally seen as more of HPC system. And when we say HPC systems, some people believe that it's less flexible. So here, Selene is really in the middle. It's really a supercomputer that has the flexibility that is required by your deep learning researcher. For example, we need to be able to build package, schedule and prioritize between different teams, have capacity on demand or on a schedule, report, I don't know, just priority dashboards, performance dashboards, and ensure reproducibility and rapid triage, right? For example, at NVIDIA, you want to push something in the tree for a DL workload. You need to make sure it passes validity at scale, right? And that validation and that at scale testing is actually done on Selene. As a new generation based on the A100 architecture, it has a lot of pretty interesting specific pods. So in a lot of NVIDIA servers, and the DGX is the flagship here, it has 8 A180 gig GPUs, right? A lot of GPU memory, system power of 6.5 kilowatt, which is significant while still being feasible for a server that size. When we built Selene, we were one of the first supercomputers having a dual AMD Rome CPU. So those CPUs have a lot of threads. So it requires to be able to handle that for performance and be able to feed the GPU. A large amount of system memory, but also a large amount of interconnect. As we discussed earlier, you mentioned, what do we need to put the systems together? They need to be able to talk to each other. So here, those 8 single port connectix NICs make sure the GPU talk to each other. And those 2 dual port connectix 6 NICs on the other side make sure all those machines can talk to the storage. And as we're going to see along the way, that flow from data to GPU and in between GPUs is actually critical to deep learning.
In fact, it's sort of one of the hallmarks of high performance computing versus just big data computing, that you have this intercluster traffic, this east-west traffic, and they have to be exchanging data at every step of computation. And you talked a little bit about deep learning just before, and that this is really designed for that. So that's fascinating. Tell me a little bit more about the Superpod itself. How does that come together?
So the Superpod. So we call a Superpod all the computers that we build based on that model, right? Basically, a Superpod is a set of 1K GPU pods, okay? And so 140 DGX A100 node form a Superpod. It's 1120 GPUs, and that's the unit you see here, right? And here you see the machine that we've seen before. I mentioned those 8 interfaces for the GPU to talk to each other, and that's what you see here in that complex networking. And you see here the storage, and you see that each machine has those 2 interfaces that we discussed that also are interconnected together to go to the storage here on that end. And basically that model is extensible because it's modular, and we can always extend all the way up to 4 gig and higher. So for us, it was very convenient because when we build Selene, we wanted to make sure we could build it incrementally, but also sell it by subsets. And that's what we did. So right now you can buy a 140 node Superpod, a 280, and so on and so forth. And you will be able to attach a second pod without dismantling the first one. It's really an extensible model. One of the additional requirements we had was that we needed to make sure that we could reach 1 terabyte per second performance for the storage fabric. And we're going to see a little bit later what that means in practice.
And that makes it a modular supercomputer, right? So this thing can be grown, I mean, almost a scaling supercomputer, which is a kind of an interesting idea in this cloud age where someone can just keep growing something as their needs grow. So let's dive into that. You mentioned the storage architecture. Tell us a little bit about what goes on at the storage layer.
Okay. So let me show you the details here. So here we have a 100 node example of what a pod would look like, right? And if you remember the previous picture, I'm basically showing the storage part of it. So for the fabric, which is the InfiniBand we built to get that storage in, we have a small subscription ratio. That means it's a factory, it's a by-rail factory with a small subscription ratio. And here is how the number of switches you will need to have depending on the size of the pod you're looking at. So for 10 nodes, 20 nodes, 40 nodes, 80 nodes, etc. And we can keep on growing this at will. So in practice, what does it look like in a rack? So in the rack, it looks basically like this. So each of the 4 pods that I've showed you before that Selene is made of actually has an own performance storage section. So here, those 2 racks are pictured here. And per GPU pod, we have those 2 racks that contains the storage IB switches. So the complex drawing you've seen actually can be just seen here as two big half racks of networking from InfiniBand. And then per pod, we have 10 DDN AI 400X appliances. All is NVMe, all is flash. We have 2.5 petabytes usable capacity per pod. So we're going to come back to that after because we combine it together. And we combine it together so that at the end of the day, we have 40 DDN AI 400X appliances for the whole Selene cluster, which gives us a 10 petabyte usable capacity that has a peak performance of 2 terabytes per second per RAID in aggregated mode and 1.5 terabytes per second in write. So that's how it overall goes together. Sorry,
I mean,
was a
I'm trying
little
to I'm
fast.
trying to add up those numbers in my head here, and I'm like, okay, those are big numbers. But that's really so. You've got 2 racks of storage per GPU pod, and you can put up 4 pods in there to get obviously 8 racks. I can do that math. And then how many racks altogether would a 4 pod Selene cluster have?
So we have. It depends on what people can do. So Selene has several. We put 4 machines per racks, right? And we have 560 nodes. So we have 128 racks of machines, then 8 racks of storage. And then we have a couple other racks. I think we have 8 racks total for InfiniBand in general. And then it depends on how people end in their management network. So our management networking is very, very light. So we just have some racks because we do most of the CI and everything is handled elsewhere. But then everybody can have what they want. So overall, in a little bit less than 150 racks, you have a full cluster. Which, if you think about it, for us was a good balance between density and not having too many problems, cooling it, racking it. We built during a pandemic. So space was a consideration, right?
Sure.
People couldn't be too close to each other. So for us, that was overall a good balance so that you can work in a section while having the other section in production.
All right, and the storage nodes that are in this picture are DDN, obviously nodes. Tell us a little bit about those from your perspective.
Okay, so those are the classical DDN AI 400X appliances. So here is an example of a configuration. So remember, we have 40 of those. We run classical is the EXAScaler, which is based on Lustre, right? We get the performance out of that. Each AI 400X is configured with 4 VMs. We have 1 NDT and 8 OST per, so that gives a total of 20 NDT and 160 OSTs in a production configuration. So people can run it differently. We found that for us, it's the best balance that we have. We use PFL to facilitate efficient striping because we have somewhat diverse set of files. And so those are, for the nerdy aspects, those are parameter. And as mentioned earlier, we rely heavily on multi-rail. So we have those 2 interfaces and both are used to provide that performance. So we're gonna see that later in benchmarks, but that's gonna show how we can get either such a good performance per node and at a small number of nodes.
All right, let's move on here to the actual performance of this thing. So you built this, you've architected it, you've got these recipes together, you've taken care of all the management complex. How well does it actually deliver?
Okay, so classical approach, application perf, synthetic, right? So nothing fancy. We run the traditional AOR setup with an IO size of 16 meg and 80 threads per client. Remember, we discussed we have a pretty beefy threading CPU, right? And so from a single client, we can nearly achieve the maximum of those 2 HDR200 connections we have, which was the objective, right? Of just leveraging those 2 rails to get the maximum performance. And here we can see an example where 16 client and above can completely saturate 10 AI 400x. So we sometimes get that question, say, hey, how about you got 40 or you got so many appliances? Is that useful? And here we're showing that as soon as you get more than 16 nodes, yes,
Okay.
it's useful. That's how you get there. And just to make sure we can go back, remember I mentioned, hey, objective was 1 terabyte per second. Can we reach that, right? And the first thing we did was validating that, and we can validate that with 20 appliances, and we use 64 clients to do that on that same test. But again, this is synthetic benchmark, right?
All right. I'm sure now you're going to tell me about some real world benchmarks.
Yes. So synthetic benchmarks are nice, right? But in practice, the engineers we have working on NVIDIA, the researchers, they don't care about my synthetic benchmark. They want to see real data. And that's what I'm going to show you here. So here, I'm going to first introduce the world we live in, right? Where HPC benchmark don't quite apply to us. So here we use heavy deep learning workloads that are known to read somewhat big number of data and also create large checkpoints. And so the first one, we use the standard, right? We start always from benchmark to standards to more exotic configurations. So here we use MLPerf training v0.7, right? And so a majority, I gave the little illustration here. So the majority of DL workload, they work the same. Basically, they read and read and read always the same amount of data in batches, right? Those batches gets processed by the GPU. Then there's a big or reduce between all those GPUs, and you rinse and repeat, and you reread that data all over again, right? So we selected 2 workloads. So that's an example with a data parallel model, but overall, that's the good first approach, right? So we selected 2 workloads from the MLPerf training benchmarks to evaluate DL performance. 2 that are very important to us. So ResNet 50, image classification model, very well known, but also BERT, natural language processing models. You've heard my accent. I can't, I just want language translation processing to get better so that I can get auto caption with no problem. Okay, so the 2 examples here, we run from the local NVMEs we have on the DGX. So the DGX have a set of very fast local NVMEs that are put together as a RAID. And we also check directly from the luster that is exposed from the EXAScaler appliances, right? And what we have is basically almost the same performance at a large scale. Why is that very important? Basically, we want to make sure, you see some articles that claim that you can't really do deep learning with a parallel file system, right? So we want to make sure we don't have our people working on a machine having to transfer data, having to bother, etc. So making sure the data can get ingested very fast is actually very important. It's actually even more important when it's a real workload. So MLPerf, you could assume it's still a benchmark, right? But here, we also took a model that is known to be I'm going to call it a little bit chubby, but it's a bigger model. I gave you here the link to the paper and the link to the repository. The idea is our ongoing researchers right now work with this kind of models. We're talking GPT-2, GPT-3, from 1 billion to 1 trillion parameters in size, right? It's an interesting use case for us because those are large models. They will create large checkpoints. So a lot of people claim that in deep learning, you never write. Actually, sometimes you need to checkpoint. Those checkpoints can be significant. They use both tensor and pipeline parallelism. So I mentioned earlier that it was only data parallel, the little drawing I've seen. Here, it's a combination of both. And it's training on a shared cluster, right? And we're very, how can I say that? We have a heavy constraint on the supercomputer. You know that wall time when you launch your job and you have to finish by a certain amount of time. We need to get use of, you take your time, you checkpoint, and then you restart again because everybody's waiting, right? The supercomputer, we want to make sure we make the best use of it. And so that's very important. So this is an example using GPT-3. So it's 13 billion as an example model, right? And the checkpoint file is our 172 gigs across 8 files, and it's over 128 nodes. And I'm going to show you curves. Basically, it was to make sure that we were capable of handling that without no problem on 128 clients. Now, remember initially I told you, hey, we need to be able to do 1 terabyte per second, right? So that's the reads, right? That's the writes. So you can see those gigabyte can be done no problem. But also, if we take a bigger model, here we go. In practice, we actually need this terabyte per second.
Okay.
And when we started design, it's like, why are you spending so much time and energy trying to design it so big iron? Just because we need to. And that was the conclusion of my long graph story. But hopefully that helps.
All right, so this thing actually delivers. So that's pretty cool. We just got a few minutes left here. Tell us about some of the things you're working on or that you're looking forward to here coming up in Selene.
Okay, so what we like very much is the idea of client caching. Let me explain that. So as I mentioned earlier, a lot of DL workloads requires reading the same data over and over again. And we had a lot of researchers and engineers say, hey, can you help me copy my data? I've been at it for 40 minutes. I don't understand what's going on. Copying data at scale is actually much more complex than it seems, right? The classical tricks don't work anymore. And so here we wanted to use the idea of caching on the client, so making sure the client could have a pre-cached copy of the datasets that are used the most often. So it's called hot nodes in DDN terminology, and it's an extension. So basically what we do is we pre-populate the datasets read-only on a partition, and the node gets a copy at first access. Here is what happens in practice. So that's a very complex graph, but allow me to spend 30 seconds on it, not 30 minutes. I know we don't have them. So basically, here is what we do. This is the first epoch in training, and we have no caching on, right? So in green is the GPU usage. In red and yellow, this is the transfer from the storage. And in blue and purple, this is the disk activity. And what you see here very quickly is the first time we train at the first epoch, the storage fabric will pull the data sets, use it to work on the GPU here, but also automatically the client caching will push that data set on the nodes, so that when you start the second epoch, the data set is already on the node and is pre-populated, and you don't have that much traffic. Which
this would make a huge difference, right? Because now deep learning is nothing but iterations of things.
Yes, and not only it prevents any challenge with having to make sure your data integrity is correct and so on and so forth. So as a user, everything's transparent. I just removed a lot of the traffic and I don't have to worry about it. And if you look at what happens, if you look at what happens in terms of performance, this is what happens when you pull from the drive. So we're assuming this is the unit that's pulling for the local drive. That's pulling from the network. So you can see we designed the network for it. So of course we're pretty fast here. But what's very important is we cut that time in two just by using client caching. So we have a 3% performance uplift. So that uplift can look at relatively moderate, but at scale, 3% over something that, so here it's a fast training, but over something that trains for hours and hours, that can start to matter.
Yeah, I think at the supercomputer level, even I think we were talking 0.5% matters, right? That's something that I come back to on here. All right, so I think we're running out of time here, Julie. Any last sort of things you want to say about Selene and the work that's available here?
So mission accomplished, that we got a 1 terabyte per second.
Okay.
That solution can be implemented on any EXAScaler cluster setup, right? So the idea of making things that we could have the world try is actually there. It's very flexible. We like that. It's very reliable and resilient. So the multi-rail approach and having all that put together makes it easier for us to maintain. There's nothing we hate more than having, to be there on the weekend to monitor the file system. We don't do that. The newer features are very well suited for DL, and we hope that a lot of people will adopt them. And I gave you 2 links about the announcement and blogs if you want to know more.
All
about
right,
it.
and those links will be available in this on the side here. Also, if you have any questions and you're in the audience, you want to type them in, please use the chat facility here. Julie, thank you for presenting this today. We've got to move on. I could talk to you all day about supercomputers, but thank you very much for being here.
Thanks so much. All the pleasure was mine.